Most nights, the universe feels completely still. We look up at the stars, and they seem frozen in place, as though nothing has changed for thousands of years. The moon rises exactly where we expect it to. The planets quietly follow their familiar paths across the sky. From Earth, the cosmos appears peaceful, almost motionless. But appearances can be deceiving. Every object we see is moving. Earth is racing around the Sun at nearly 30 kilometers every second. The Sun itself is orbiting the center of the Milky Way at more than 800,000 kilometers per hour. Every nearby star is following its own journey through the galaxy, each traveling in a different direction at a different speed. The universe has never been standing still. It only feels that way because the distances involved are so enormous. Hidden among those countless moving objects are things we cannot see at all. Rogue planets drift through interstellar space without a parent star. Cold clouds of hydrogen stretch for hundreds of light years, almost completely invisible against the darkness. And scattered throughout the Milky Way are millions, perhaps hundreds of millions, of black holes, wandering silently through the galaxy after being born from the deaths of massive stars. Most of them travel alone. They emit almost no light. They make no sound. Unless they happen to pass near another object, they remain completely invisible, crossing the galaxy unnoticed for millions of years. Now imagine that one of those invisible travelers has just been discovered. Not because someone finally saw the black hole itself, but because astronomers noticed something strange happening to the stars behind it. A distant star suddenly appeared brighter than expected. Another seemed to shift slightly from its predicted position. At first, the observations looked unrelated. Small measurement errors happen all the time. Telescopes are affected by Earth's atmosphere, tiny imperfections in detectors, and countless other sources of uncertainty. But as more observatories collected data, a pattern slowly began to emerge. Every strange observation pointed toward the same region of space. Something massive was moving there. Something completely invisible. Within weeks, observatories around the world began focusing their telescopes on the same tiny section of the sky. Computer models tested every possible explanation. A hidden star? The numbers didn't fit. A rogue planet? Far too small? A cloud of dark matter. The gravitational signature was too concentrated. One possibility remained, and with every new observation it became more likely. A lone stellar black hole. The announcement spread through the astronomical community almost immediately. For most scientists, it was exciting rather than frightening. Finding an isolated black hole would be a remarkable discovery. These objects are notoriously difficult to detect because they produce almost no light of their own. Every new one helps researchers understand how stars live, die, and evolve throughout the galaxy. Then another calculation was completed. The black hole was moving. That was expected. Everything in the galaxy moves. But the direction of that motion was unexpected. Instead of crossing harmlessly through some distant part of the Milky Way, its trajectory appeared to intersect our own region of space. At first, nobody was concerned. The galaxy is unimaginably large. An object can head generally toward the solar system while still passing hundreds or even thousands of light years away. Astronomers refined their calculations and waited for additional observations. Months passed. The uncertainty became smaller. The path became clearer. Every update produced almost the same result. The black hole wasn't simply moving toward our part of the galaxy. It was moving toward the solar system itself. The news never reached the public immediately. Scientists have learned to be cautious. Extraordinary discoveries require extraordinary evidence, and orbital calculations improve every time new observations become available. No one wanted to announce the greatest astronomical discovery in modern history only to discover a small error in the measurements. More telescopes joined the effort. Space-based observatories were directed toward the object. Supercomputers generated millions of possible trajectories. Most of those simulations ended with exactly the same conclusion. The black hole would pass through our solar system. No one yet knew exactly how close it would come. That single detail would determine everything. A distant passage might only disturb a few comets at the edge of the sun's influence. A closer one could reshape the orbits of the planets themselves. An even closer encounter could become one of the greatest natural disasters in the history of the Milky Way. For the first time since humanity learned that Earth was not the center of the universe, our entire solar system had become part of a cosmic prediction. Governments quietly contacted leading observatories. Space agencies began sharing information that had once remained confined to research institutions. Additional satellites were tasked with observing the approaching object. Although no public announcement had yet been made, preparations had already begun. The strange part was that nothing looked different. Children still played outside. Airplanes crossed the sky. Cities remained brightly lit every evening. The sun rose exactly as it always had. The universe gave no visible indication that anything extraordinary had been discovered. Somewhere beyond the darkness, an invisible object several times more massive than the sun continued drifting silently toward us, completely unaware that an entire civilization had just begun watching its approach. The question was no longer whether the black hole existed. The question was whether humanity had found it early enough. Because although black holes are invisible, their gravity is not. And gravity always arrives before the black hole itself. The first public announcement was surprisingly calm. There were no emergency broadcasts. No evacuation orders. No predictions of immediate disaster. Instead, the world's largest observatories held a joint press conference explaining that astronomers had discovered a previously unknown stellar black hole whose trajectory would carry it into the solar system. They emphasized that the object remained extraordinarily far away and that there was no immediate danger to Earth. Most importantly, they explained that gravity weakens rapidly with distance. Simply moving toward the solar system did not automatically mean catastrophe. For a few days, many people ignored the story. It sounded too unbelievable. Others confused it with science fiction or assumed it had been exaggerated by the media. But curiosity spread quickly. Every news channel invited astrophysicists to explain what a black hole actually was. Internet searches exploded. Planetariums filled with visitors. Schools replaced ordinary science lessons with discussions about gravity, stars, and the structure of the universe. Overnight, millions of people found themselves fascinated by an object they could not even see. Behind the scenes, astronomers were far busier than television audiences realized. Every observation slightly improved the predicted orbit. Modern telescopes could measure tiny changes in the positions of distant stars with astonishing precision, allowing scientists to determine the black hole's path more accurately each week. The uncertainty surrounding its future location slowly disappeared. Then came the first, truly unsettling result. The black hole would not merely pass near the solar system. It would enter it. That announcement changed everything. The solar system is much larger than most people imagine. Neptune orbits nearly 4.5 billion kilometers from the Sun, yet even that enormous distance represents only a tiny fraction of the Sun's gravitational influence. Far beyond the planets lies the Oort cloud, a vast shell of frozen objects stretching almost halfway to the nearest stars. If the black hole entered this region, it would technically be inside the solar system long before it came anywhere near Earth. That realization brought a small sense of relief. Even after entering the solar system, the black hole would still remain unimaginably far away. Humanity would have time to watch, study, and prepare. Scientists now focused on one question above all others. How close would it come? Every million kilometers mattered. If the black hole remained in the distant outskirts of the solar system, its effects might be limited to disturbing long-period comets. If it traveled farther inward, the giant planets would begin responding. Closer still, and the inner planets, including Earth, would eventually feel its gravity. As the weeks turned into months, the answer slowly emerged. The projected path kept shifting. Not outward. Inward. Each refinement placed the black hole just a little closer to the Sun than the previous calculation. No single update caused panic. Taken together, however, they painted an increasingly uncomfortable picture. The object was heading toward the planetary region. The world's greatest supercomputers began running continuous simulations. Millions of possible futures were calculated, each using slightly different assumptions about the black hole's exact mass and velocity. Scientists watched those virtual solar systems evolve over decades and centuries, searching for the smallest clues about what would happen next. Most of the simulations agreed on one thing. The first victims would not be planets. They would be the countless frozen worlds waiting at the edge of the solar system. Long before Earth experienced any measurable effects, the distant Oort cloud would begin changing. Ancient comets that had remained undisturbed since the birth of the solar system would slowly receive tiny gravitational nudges, sending some drifting into interstellar space while others began long inward journeys toward the Sun. The countdown had begun. Not because Earth was already in danger, but because the solar system itself had started waiting for a visitor unlike any it had encountered in billions of years. For now, humanity could do little more than watch. The invisible traveler continued moving silently through the darkness. Every day it came slightly closer. Every day the calculations became more precise. And somewhere at the frozen edge of the Sun's domain, the first pieces of our cosmic neighborhood were about to feel a new force that had traveled across the galaxy for millions of years before finally arriving at our doorstep. In the next chapter, the black hole reaches the outer frontier of the solar system, where the oldest and most distant objects orbiting the Sun become the first witnesses to its arrival. The edge of the solar system is unlike anything most people imagine. Beyond the familiar planets lies a region so vast that sunlight becomes little more than an unusually bright star. Temperatures hover only a few degrees above absolute zero, and countless frozen worlds drift through complete darkness, each following an orbit that may take hundreds of thousands or even millions of years to complete. These distant objects have remained almost untouched since the birth of the solar system over 4.5 billion years ago. They have survived asteroid impacts, nearby supernovae, and the slow evolution of the Milky Way itself. For all that time, their motion has been governed almost entirely by one object, the Sun. That quiet balance is about to change. The black hole reaches the outermost boundary of the Sun's gravitational influence. It is still incredibly far from the planets, but distance is no longer enough to hide its presence. One by one, the frozen bodies of the distant Oort cloud begin experiencing tiny changes in their motion. Most of these changes are so small that they would be impossible to notice over a human lifetime. But astronomers are not watching for hours or days. They are watching a system that has remained stable for billions of years. The first evidence comes from the comets. Long-period comets normally appear only occasionally, arriving from every direction after spending millions of years in deep space. Now the number slowly begins to increase. At first, only a few more than expected are discovered. then dozens, then hundreds. Their paths all point back toward the same distant region where the invisible black hole continues its steady approach. None of these comets are dangerous by themselves. Most will never come anywhere near Earth. But together they reveal something remarkable. The outer solar system has started responding to the new gravitational visitor. Astronomers compare it to watching leaves floating on a still pond. Toss a small stone into the water, and the leaves do not move immediately. The ripples travel outward first, gently disturbing one leaf after another until eventually the entire surface responds. The approaching black hole is creating similar ripples, except instead of moving through water, they move through gravity itself. For the first time, humanity is not simply predicting what the black hole will do. It is watching it happen. The scientific community becomes increasingly confident in its models. Every disturbed comet behaves almost exactly as expected. Every new observation confirms the calculations. While the public continues following the story with curiosity, researchers understand that something much more significant has happened. The black hole has officially entered the solar system. Technically, it crossed that boundary months earlier when it reached the outermost edge of the Oort cloud. But now its influence can no longer be dismissed as theoretical. It has become measurable. Around the world, space agencies begin discussing missions that only months earlier would have sounded impossible. Could probes be launched to study the black hole from a safe distance? Could instruments measure its gravity directly? Could humanity gather scientific data that would transform our understanding of one of the universe's greatest mysteries? For scientists, this is both the greatest opportunity and the greatest danger in history. Never before has a black hole approached close enough to study in such detail. Never before has one threatened the home of the observers studying it. Meanwhile, life on Earth remains almost completely normal. Cities continue growing. Businesses open each morning. Sports stadiums fill with cheering fans. Weddings, birthdays, and ordinary conversations continue exactly as before. It feels strange that something capable of reshaping the solar system could exist while everyday life carries on without interruption. Yet that is often how the universe works. The greatest events begin silently. The black hole still cannot be seen through any telescope. If you looked toward its position in the sky, you would see only darkness and distant stars. But behind that darkness, gravity continues doing exactly what gravity has always done. It reaches outward. Patiently. Relentlessly. And every passing day, it reaches a little farther. Eventually, the first planet will begin to notice. Not Earth. Not Mars. But the giant that has shaped the solar system for billions of years. Jupiter. If the Sun is the king of the solar system, Jupiter is its greatest guardian. More than twice as massive as every other planet combined, Jupiter's gravity has influenced the architecture of our planetary system since its formation. Countless asteroids have been captured, redirected, or thrown into interstellar space because of its enormous mass. Some scientists even believe Jupiter helped protect Earth throughout history by deflecting objects that might otherwise have struck our planet. For billions of years, Jupiter has been the dominant gravitational force beyond the asteroid belt. Now, for the first time, another object is beginning to compete with it. The change does not happen overnight. Jupiter continues following its familiar 12-year orbit around the Sun, surrounded by its dozens of moons and wrapped in enormous storms larger than Earth itself. Anyone standing on one of its icy moons would notice nothing unusual. The clouds continue moving. Lightning flashes through the atmosphere. The great red spot remains locked in its centuries-old storm. But astronomers are measuring something different. Every planet follows an orbit that can be predicted with extraordinary precision. Tiny corrections are always necessary because every planet pulls on every other one, but these interactions are well understood. Now Jupiter begins arriving at certain positions in its orbit just slightly earlier than expected. The difference is tiny, measured at first in fractions of a second. Then the difference grows. It is still far too small for anyone to notice without powerful computers, yet it matches almost perfectly what scientists predicted months earlier. The black hole has reached the point where even Jupiter can no longer ignore it. This discovery marks a turning point in the story. Until now, every measurable effect involved distant comets and frozen objects at the edge of the solar system. Those places feel remote from human experience. Jupiter is different. Everyone knows Jupiter. School children recognize its striped clouds and giant storms. Seeing the largest planet in the solar system respond to the approaching black hole suddenly makes the threat feel much more real. The changes extend beyond Jupiter itself. Thousands of asteroids trapped in stable regions around the giant planet begin drifting ever so slightly from their ancient paths. Some move inward. Others move outward. Most remain harmless, but astronomers immediately recognize the pattern. The solar system is beginning to reorganize itself. Not dramatically. Not chaotically. But undeniably. Saturn soon follows. Its orbit, too, begins showing tiny discrepancies. Uranus and Neptune respond more slowly because of their greater distances and orbital periods, yet the same trend eventually appears there as well. Planet after planet confirms the same conclusion. The invisible visitor is steadily rewriting the gravitational balance that has existed since before Earth had oceans. Scientists now update their simulations almost daily. Every new observation improves the prediction of what will happen next. The uncertainty surrounding the black hole's future path continues shrinking, and unfortunately, the news is not improving. The closest approach is becoming closer. Not by enormous amounts. But enough. Enough to ensure that the influence will eventually spread beyond the giant planets. Beyond the asteroid belt. Toward the inner solar system. Toward Earth. The realization changes the mood around the world. There is still no panic, because nothing dangerous is happening yet. But governments begin treating the event as more than an astronomical curiosity. New observatories are funded almost immediately. Military satellites quietly assist civilian astronomers by providing additional tracking data. International cooperation reaches levels rarely seen outside of global emergencies. Everyone wants the same thing. Better predictions. Because prediction is the only advantage humanity has. The black hole cannot be stopped. It cannot be pushed away. But it can be understood. As months pass, another unexpected consequence appears. Bright comets begin decorating Earth's skies more frequently than anyone can remember. Some remain visible for weeks, their glowing tails stretching across the night. To most people they are beautiful. To astronomers they are messages. Every comet is another reminder that the outer solar system is changing. Every observation confirms the same truth. The black hole is still coming. And although Jupiter was the first planet to respond, it will not be the last. Soon, the effects will reach the one companion that has shaped Earth's history more than any other object besides the Sun, the Moon. And once the Moon begins to change, humanity will no longer need telescopes to know that something extraordinary is happening. For as long as humans have existed, the Moon has been one of the few constants in our lives. Long before calendars, clocks, or telescopes, people measured time by its phases. Farmers planted crops according to its cycle. Sailors trusted its tides. Entire civilizations built myths around its quiet journey across the night sky. Although we rarely think about it, the moon has always been far more than a beautiful object in the sky. It has helped stabilize Earth's rotation for billions of years, preventing our planet from wobbling chaotically as it spins through space. Without the moon, life on Earth may have evolved very differently. Now, for the first time since it formed, the moon begins responding to a new master. The change is almost impossible to notice at first. Scientists using lasers to measure the moon's exact distance detect a discrepancy only a few centimeters larger than expected. The measurements are repeated dozens of times using different observatories around the world. The equipment is recalibrated. Atmospheric conditions are carefully analyzed. Yet every result points toward the same conclusion. The moon is no longer following precisely the orbit it has traced for centuries. To most people, this sounds insignificant. A few centimeters over nearly 400,000 kilometers hardly seems worth discussing. But astronomers know that the moon is one of the most carefully measured objects in the solar system. If its orbit is changing, then the invisible black hole is no longer influencing only distant planets. It is beginning to influence Earth itself. For several months, nothing appears different in the sky. The moon still becomes full every 29.5 days. Eclipses continue according to predictions that have been refined over generations. Children still point toward the same familiar craters. If you stepped outside on a clear evening, you would never guess that the Earth-Moon system had already begun changing. Then the tides begin behaving strangely. At first, the changes are so small that only oceanographers notice them. Some high tides arrive slightly earlier than expected. Others reach levels a few centimeters above long-term predictions. Storm surges become just a little more destructive because they now ride on unusually high tides. Coastal monitoring stations record tiny differences that gradually become too consistent to dismiss as coincidence. The oceans are responding to the same force that is pulling on the moon. Water has always been the first part of Earth to react to changing gravity. It flows more easily than rock, adjusting continuously to the gravitational forces acting upon it. The moon has controlled this rhythm for billions of years. Now another influence has quietly entered the system. People living near the coast begin noticing that familiar beaches no longer look quite the same. Certain sandbars disappear more frequently. Some harbors require constant dredging because changing currents redistribute sediment in unexpected ways. Fishermen who have spent decades reading the tides begin commenting that something feels different, even if they cannot explain exactly what it is. Most people still refuse to believe that a black hole could be responsible. After all, the object remains invisible. It is still unimaginably far away. How could something that distant already be affecting Earth? Scientists patiently explain the same principle again and again. Gravity does not suddenly switch on when an object arrives nearby. It extends across space forever, becoming weaker with distance but never completely disappearing. As the black hole slowly moves closer, its influence gradually grows stronger. The process resembles someone slowly turning a dial rather than flipping a switch. Meanwhile, another subtle change appears. Earth's rotation becomes ever so slightly less predictable. Modern civilization depends on extraordinarily accurate timekeeping. Atomic clocks measure time so precisely that they would lose less than a second over millions of years. These clocks reveal tiny natural changes in Earth's rotation caused by earthquakes, shifting ice sheets, ocean currents, and atmospheric circulation. Now scientists notice another small contribution. The changing gravitational relationship between Earth, the Moon, And the approaching black hole is altering the planet's rotation by amounts far too small for humans to feel but large enough for instruments to detect. The effect fascinates physicists because it demonstrates something remarkable. The black hole has not arrived. It has not even reached the inner solar system. Yet humanity is already measuring its influence on our own planet. Around the world, scientific observatories expand their monitoring programs. Thousands of additional sensors are installed along coastlines. New satellites are launched specifically to measure Earth's changing gravitational field with greater accuracy. Never before has humanity observed an event like this, and every new measurement becomes another piece of one enormous scientific puzzle. Public opinion slowly begins changing as well. At first, many people dismissed the black hole as another sensational news story. But as years pass and the predictions continue proving correct, skepticism gradually fades. Every scientific forecast has come true so far. The increased number of comets arrived exactly when expected. Jupiter's orbit changed almost precisely according to the computer models. Now the Moon itself is behaving exactly as predicted. The calculations have earned humanity's trust. Unfortunately, they also contain increasingly troubling news. The black hole continues moving inward. Every updated simulation reduces the uncertainty surrounding its path. Every new observation places it slightly closer than anyone hoped. Scientists no longer spend most of their time debating whether the black hole will affect Earth. Instead, they focus on a far more difficult question. When will the effects become impossible for everyone to ignore? The answer is surprisingly close. Because while the Moon is the first familiar object to respond visibly, it will not be the last. The next changes will not involve the natural world alone. They will begin affecting the technology that modern civilization depends upon every single day. Modern civilization is built on precision. Airplanes cross continents because satellites tell them exactly where they are. Cargo ships navigate oceans using signals transmitted from space. Financial markets depend on atomic clocks synchronized across thousands of kilometers. Weather satellites watch storms develop before they reach land, while communication satellites quietly connect billions of people every second of every day. Most of us never think about these systems because they work so reliably. Now they begin making small mistakes. The first signs appear in satellites orbiting Earth. Engineers notice that routine orbital corrections are becoming slightly more frequent than expected. Normally these adjustments compensate for atmospheric drag, solar radiation, and the familiar gravitational influences of Earth, the Moon, and the Sun. Now another force has quietly entered the calculations. The satellites are still safe. They still perform their missions. But every month, they require just a little more correction than before. The effect spreads to navigation systems. GPS satellites depend on incredibly precise timing. Their onboard atomic clocks already account for Einstein's theory of relativity because time passes slightly differently in orbit than it does on Earth's surface. Now software engineers introduce yet another correction into their calculations. Most people never notice because the adjustments happen automatically, but behind the scenes thousands of engineers are rewriting navigation models to include the approaching black hole. Space agencies become some of the busiest organizations on Earth. Every active spacecraft suddenly becomes a valuable scientific instrument. Probes traveling toward Mars, Jupiter, and beyond continuously transmit data that helps scientists measure the changing gravitational environment throughout the solar system. Even satellites launched decades earlier contribute useful information simply by following their slightly altered orbits. The International Space Station becomes one of the most closely watched laboratories in history. Astronauts cannot feel the black hole's influence directly because everything around them is accelerating together, but their instruments detect tiny differences in orbital motion that grow steadily with time. Every experiment confirms what astronomers have been saying for years. Gravity is changing. Not dramatically. Not suddenly. But unmistakably. On Earth, life continues much as before. People still drive to work, children still attend school, and cities remain filled with ordinary routines. Yet there is a growing awareness that something historic is unfolding beyond the atmosphere. News broadcasts no longer ask whether the black hole is real. Instead, they discuss the latest measurements and updated predictions with the same regularity once reserved for weather forecasts. Universities begin offering public lectures every week. Planetariums become crowded with visitors eager to understand the approaching object. Astronomy, once considered a niche subject, suddenly becomes one of the most discussed sciences on Earth. Millions of people who had never thought about gravity beyond dropping an apple now find themselves learning about orbital mechanics and Einstein's theories. The black hole has done something unexpected. It has made humanity look up. Meanwhile, the scientific picture continues becoming clearer. Every planet is now responding exactly as expected. The giant planets have already shifted slightly from their ancient paths. The Moon's orbit continues drifting by tiny but measurable amounts. Earth's tides have become less predictable than at any other point in recorded history. None of these changes threatens civilization immediately, but together they tell one unmistakable story. The solar system is no longer in equilibrium. Imagine a perfectly balanced mobile hanging from a ceiling. Touch one piece very gently, and nothing dramatic happens at first. But over time every other piece begins moving as well because they are all connected. The solar system works in much the same way. No planet exists in complete isolation. Every orbit depends, however slightly, on every other orbit. The black hole has not shattered that balance. It has nudged it. And the entire system is responding. Then astronomers notice another consequence. The asteroid belt between Mars and Jupiter begins behaving differently. Most asteroids remain exactly where they have always been, but a handful receive tiny gravitational nudges as Jupiter's orbit slowly changes. These changes are not immediately dangerous, yet they remind scientists that the effects of the black hole are spreading from one region of the solar system to another like ripples across a pond. For the first time, emergency planners begin considering scenarios that had previously belonged only in scientific papers. Governments review the resilience of communication networks, electrical grids, and transportation systems. Space agencies prioritize missions that improve understanding rather than exploration. The world's greatest supercomputers run almost continuously, updating simulations as fresh observations arrive every day. The results remain remarkably consistent. There is still no way to stop the black hole. There is still no realistic method of changing its course. Humanity's greatest advantage remains knowledge. Every additional day of observation makes the future slightly less uncertain. Every new measurement helps answer another question. Yet the calculations also reveal something unsettling. The period of slow, almost unnoticeable change is nearing its end. Until now, gravity has touched only the systems surrounding Earth. Very soon, it will begin affecting Earth itself. Not through satellites. Not through computers. Not through scientific instruments. Through the planet. The oceans will be the first to respond in ways that ordinary people can no longer ignore. Coastlines that have remained stable for generations will begin changing. The familiar rhythm of the tides will slowly disappear. What began as tiny corrections measured by scientists will become visible to anyone standing beside the sea. The invisible traveler is still hidden in the darkness beyond the giant planets. No telescope shows a growing black circle in the sky. No warning sirens echo across the earth. Yet every passing day, gravity grows just a little stronger. And the countdown to Earth's final chapter quietly continues. For years, humanity has lived with the knowledge that an invisible black hole is moving toward the inner solar system. What began as a distant astronomical discovery slowly became part of everyday life. Scientists refined their predictions. Engineers adapted satellites and navigation systems. Governments quietly prepared for possibilities that had never before existed outside theoretical physics. Through it all, the most remarkable thing was how ordinary life remained. People still celebrated birthdays, watched sunsets, planted gardens, and planned for the future. The universe often changes, slowly enough that life continues almost unaware. That period is finally coming to an end. The latest observations leave very little uncertainty. The black hole has crossed the orbit of the giant planets and is now approaching the region occupied by the rocky worlds. It remains invisible, but every calculation confirms that its gravity is becoming stronger far more quickly than before. The countdown is no longer measured in centuries. It is measured in years. The first unmistakable changes appear along Earth's coastlines. Tides that once differed by only a few centimeters now rise noticeably higher than historical records ever predicted. During certain lunar cycles, seawater floods streets that had never previously experienced high tides. Some coastal communities begin constructing temporary barriers, believing the changes might still stabilize. Others quietly begin relocating critical infrastructure farther inland. The oceans are responding exactly as scientists predicted, but watching those predictions become reality is far different from reading them on paper. What surprises people most is that the changes are not dramatic in the Hollywood sense. There is no giant wall of water racing across continents. Instead, nature becomes increasingly unfamiliar. Harbors no longer behave according to centuries-old tidal tables. Fishing communities notice unusual currents carrying different species into waters where they have never been seen before. Coastal erosion accelerates as shorelines experience stronger and longer-lasting tides. One small change follows another until eventually everyone realizes that the sea itself is behaving differently. Far beneath the oceans, the Earth also begins responding. Every planet experiences what scientists call solid body tides. Even today, the Moon gently stretches Earth's crust by several centimeters every day, although we never notice because the movement is so gradual. As the black hole approaches, these tiny deformations slowly increase. Sensitive monitoring stations installed across the globe begin recording unusual stresses developing within Earth's crust. Mountain ranges flex by tiny amounts. Deep faults experience changing pressure. None of these changes immediately causes catastrophe, but geologists understand what they mean. The entire planet is beginning to stretch. Earthquakes become slightly more common over the following months. Most are relatively small, but their distribution looks different from anything recorded in modern history. Fault lines that had remained quiet for centuries suddenly become active, while some traditionally active regions experience less movement than expected. It is not that the black hole is creating earthquakes directly. Rather, it is changing the balance of stresses already stored within Earth's crust, gently encouraging faults that were already close to slipping. Volcanologists notice similar patterns. A handful of dormant volcanoes begin showing signs of renewed activity. Instruments measuring ground deformation detect magma systems adjusting beneath the surface. Again, nothing explodes overnight. Instead, Earth's interior slowly responds to the changing gravitational environment. The scientific community now agrees that humanity has entered a completely new stage of the encounter. Until now, the black hole had been changing the solar system. Now it is changing Earth. Space agencies continue monitoring every available satellite. Some older satellites are intentionally retired because maintaining their precise orbits has become increasingly difficult. Others consume fuel much faster than expected as engineers repeatedly adjust their paths. Navigation systems continue operating, but only because thousands of specialists constantly update the software that keeps them accurate. Modern civilization is quietly fighting a battle against changing gravity, one calculation at a time. Public anxiety naturally grows. People begin asking questions that scientists cannot answer with perfect certainty. Will the changes stop? Could the black hole pass slightly farther away than expected? Has any computer simulation shown a scenario where Earth escapes serious damage? Researchers answer honestly. The uncertainty surrounding the exact distance still exists. But it is shrinking. And unfortunately, every new observation points toward the same conclusion. The closest approach will be closer than anyone hoped. That realization changes the conversation around the world. The focus shifts from preventing disaster to understanding how much time remains. Emergency planning no longer concentrates only on protecting infrastructure. It begins considering the long-term survival of civilization itself. Underground data centers are expanded to preserve human knowledge. Seed banks receive renewed attention. Space agencies discuss whether crews stationed on the Moon or Mars could continue operating independently if Earth became increasingly unstable. Yet one uncomfortable truth becomes impossible to ignore. If Earth itself cannot survive, neither can the civilization built upon it. The black hole continues moving inward. Its speed has not changed. Its path has not changed. Only the distance between it and Earth has changed. And that distance is becoming smaller every single day. Scientists now focus almost entirely on tidal forces. They explain repeatedly that gravity itself is not the greatest danger. If Earth somehow orbited a black hole at a safe distance, life could theoretically continue much as it does around the Sun. The problem is not simply gravity. It is the difference in gravity. The side of Earth closest to the black hole experiences a slightly stronger pull than the opposite side. As long as that difference remains small, the effects are manageable. But every million kilometers the black hole travels inward increases the difference. At some point, Earth's own gravity can no longer keep the planet perfectly balanced. The process begins so gradually that no one can identify the exact day it starts. There is no single moment when everything changes. Instead, one week looks only slightly different from the previous one. Then another. Then another. Until eventually humanity realizes it has crossed an invisible threshold. The Earth that has existed for billions of years is no longer the same planet. And the worst is still ahead. Because what the black hole has done to the oceans, it will soon begin doing to the entire planet. There comes a moment when every prediction made over the previous years finally converges. The calculations from observatories, satellites, and supercomputers all point to the same unavoidable conclusion. The tidal forces produced by the approaching black hole are no longer small corrections added to the equations of planetary motion. They have become the dominant force, shaping Earth's future. The transformation begins with the oceans. The tides that had gradually grown stronger over the years now become extraordinary. Coastlines experience flooding unlike anything recorded in human history. Entire bays remain submerged long after the moon has moved overhead, because the moon is no longer the only significant source of tidal forces. The oceans are responding to a gravitational pull that grows stronger with every passing hour. Massive currents begin redistributing water across the planet. Coastal ecosystems collapse as saltwater pushes farther inland than ever before. Islands disappear beneath rising seas not because of climate change, but because gravity itself is rearranging the oceans. Shipping becomes nearly impossible as familiar tidal patterns vanish completely. Ports built over centuries lose their usefulness almost overnight. Then the solid Earth follows. The crust has resisted enormous forces since the planet first formed. Continents have collided, mountains have risen, and earthquakes have reshaped landscapes countless times. Yet all of those events occurred while Earth's own gravity held the planet together. Now another force is becoming stronger than the one that has governed our world for over 4 billion years. The side of Earth nearest the black hole accelerates ever so slightly faster than the opposite side. At first, the difference is measured in tiny fractions. Then it doubles. Then doubles again. The stretching becomes impossible to ignore. Scientists watching from the remaining observatories see something they had only witnessed inside computer simulations. The planet itself begins changing shape. Earth is no longer a nearly perfect sphere. It becomes slightly elongated along the direction of the black hole's pull. The difference is small compared to the size of the planet, yet unmistakable. Mountains experience stresses they were never formed to withstand. Valleys slowly deform. Deep beneath the surface, enormous pressures redistribute themselves throughout the mantle. Earthquakes occur continuously across nearly every major fault system. Volcanoes erupt in regions that had remained dormant throughout recorded history. Modern civilization cannot adapt quickly enough. Power grids fail as transmission lines repeatedly suffer earthquake damage. Roads fracture faster than they can be repaired. Airports become unusable. Communication networks slowly disappear, satellites exhaust their remaining fuel attempting to maintain unstable orbits. Yet the most remarkable aspect of the disaster is its silence. The black hole itself remains invisible. No enormous object fills the sky. The sun still shines. Clouds continue drifting overhead. To someone unaware of the science, the disasters might appear unrelated. Only those who understand gravity know that every earthquake, every unusual tide, and every changing orbit is part of the same unfolding event. As the distance continues shrinking, scientists realize another threshold is approaching. The tidal force is now becoming significant even across the height of a human body. For years they had explained that black holes do not pull everything equally. They pull more strongly on whatever is closer. Now that difference is growing large enough to matter on everyday scales. Standing upright becomes subtly uncomfortable. Extremely sensitive medical instruments begin measuring tiny changes in blood circulation caused by minute differences in gravitational pull between different parts of the body. These effects remain small compared to the destruction already affecting the planet, but they represent something profound. The black hole is no longer only stretching Earth. It is beginning to stretch everything on it. Physicists call this process spaghettification, a strange name for one of the most extraordinary consequences of general relativity. It does not happen instantly, nor does it resemble the dramatic scenes often shown in movies. Instead, it is the inevitable result of tidal forces continuing to grow stronger as the distance to the black hole decreases. Fortunately, for humanity, something else happens first. Earth reaches its limit. No planet can survive indefinitely while being stretched by forces greater than its own gravity can resist. Long before every individual object experiences extreme tidal forces, the planet itself begins losing its structural integrity. The crust fractures on unimaginable scales. The mantle flows in directions never before possible. Oceans no longer resemble oceans but vast moving masses responding directly to the black hole's pull. Eventually, the difference in gravity across Earth's diameter becomes greater than the force holding the planet together. The outcome is no longer uncertain. Earth begins to come apart. Not in a single explosion. Not in one dramatic instant. But piece by piece. Enormous fragments separate from the planet while remaining trapped within the black hole's gravitational field. Mountains, oceans, atmosphere, and molten rock all follow different paths depending on their positions and velocities. What had once been a living world becomes an expanding stream of debris stretching through space. The planet that spent more than 4 billion years orbiting the Sun has ceased to exist. Yet the black hole remains unchanged. It neither explodes nor grows visibly larger. It simply continues following the same path it has traveled for millions of years. Its gravity has done exactly what gravity always does. Nothing more. Nothing less. Our journey, however, is not over. Earth has reached its end, but the greatest mystery of the black hole still lies ahead. What would happen if, instead of remaining on the planet, someone had been watching from a spacecraft? What would they actually see as they continued falling toward the event horizon? Would time really slow down? Would the universe appear to stop? Could anyone ever witness themselves crossing the point of no return? In the next chapter, we leave the fate of Earth behind and follow a lone observer on the final journey toward the black hole itself, where some of the strangest predictions ever made by modern physics begin to unfold. Earth is gone. The oceans, continents, mountains, and every trace of the civilization that once covered the planet have become part of a long stream of debris slowly spiraling toward the black hole. Yet our journey does not end with Earth's destruction. Instead, we imagine that one spacecraft had left the planet years earlier, long before the final approach. Its mission was never to escape. It was built to answer one question that humanity had wondered about for generations. What really happens if you fall into a black hole? The spacecraft carries no crew. Instead, it is filled with cameras, atomic clocks, radiation detectors, and instruments designed to keep transmitting data for as long as physics allows. Every second, it sends information back toward the remaining observatories, scattered throughout the solar system. The closer it moves to the black hole, the more valuable every transmission becomes. At first, the journey feels surprisingly ordinary. The spacecraft accelerates naturally as gravity pulls it inward. There is no sudden impact, no violent shaking, and no invisible walls surrounding the black hole. If someone were standing inside, they would actually feel weightless because they, along with the spacecraft, would be falling freely through space. This is one of Einstein's most remarkable discoveries. Gravity does not necessarily feel like a force while you are falling. It simply changes the path you follow through space-time. The stars outside the spacecraft slowly begin changing. Those directly behind the black hole appear distorted, their light bending around the invisible object before reaching the spacecraft. Entire constellations seem stretched into strange arcs. Some stars appear in places where they should not exist, while others seem brighter than before because their light has been focused by gravity like a gigantic cosmic magnifying glass. The closer the spacecraft moves, the more dramatic the view becomes. The black hole itself remains perfectly dark. It reflects nothing. It emits almost no visible light. Everything beautiful comes from what surrounds it. Light from distant galaxies wraps around the darkness. Brilliant rings appear where space itself bends the paths of photons. If the spacecraft slowly rotates, the entire universe seems warped into shapes that no human eye has ever witnessed before. Meanwhile, something equally extraordinary is happening far away. Scientists watching from a safe distance continue receiving the spacecraft's radio transmissions. At first, the signals arrive exactly once every second. Then they begin arriving just slightly farther apart. Not enough for anyone to notice immediately, but enough for atomic clocks to measure with incredible precision. Time itself is beginning to change. According to Einstein's theory of general relativity, gravity does more than attract objects. It also changes the rate at which time passes. The stronger the gravitational field, the more slowly time flows relative to someone farther away. This effect is real. In fact, engineers already account for it every day when operating GPS satellites because their clocks run slightly faster than clocks on Earth's surface. Near a black hole, however, the effect becomes enormous. Imagine watching the spacecraft through an impossibly powerful telescope. Every second that passes on board appears slightly longer than the previous one. Its clocks seem to slow. The movements of its instruments become more gradual. Radio signals lose energy as they struggle to climb away from the intense gravity surrounding the black hole. To the scientists observing from afar, it almost seems as though the spacecraft is moving through time itself more slowly than the rest of the universe. Inside the spacecraft, however, nothing unusual is happening. If there were an astronaut on board, their heartbeat would feel perfectly normal. Their watch would tick exactly once every second. They could drink a cup of coffee, read a book, or conduct experiments without noticing anything unusual about the passage of time. This is one of the strangest consequences of relativity. Two observers can experience time differently, yet both are correct. There is no contradiction because time is not universal. It depends on motion and gravity. Near a black hole, these differences become so large that they completely change how two observers describe the same event. Eventually, the spacecraft approaches the event horizon. Popular movies often show this boundary as a glowing ring or swirling wall that tears objects apart the instant they touch it. Reality is much stranger. The event horizon is invisible. If the black hole is large enough, crossing it may produce no immediate sensation at all. There is no sign saying you have arrived. No sudden flash of light. No physical surface floating in space. The spacecraft simply continues falling. From the perspective of the instruments on board, nothing special marks the exact crossing. But for the observers far away, something extraordinary happens. The spacecraft never appears to cross. Instead, it slows more and more as it approaches the horizon. Its signals become weaker, redder, and farther apart. Eventually they become so faint that no telescope can detect them any longer. To the outside universe, it is as though the spacecraft simply fades into darkness without ever reaching the boundary. Yet on board, the journey continues. The spacecraft has crossed the point of no return. No engine ever built could reverse its course. No beam of light could carry a message back. Every possible future now leads deeper inside the black hole. For the first time since our story began, there is no longer any path back to the universe we once knew. The only direction left is inward. Crossing the event horizon is not the end of the journey. It is the beginning of the greatest mystery in modern physics. Everything outside the black hole can be described remarkably well using Einstein's theory of general relativity. The motions of planets, the bending of light, the slowing of time, and even the existence of gravitational waves all emerge naturally from the same elegant equations. Those equations have passed every experimental test for more than a century. Then they predict something extraordinary. At the center of the black hole lies a singularity. According to general relativity, all the matter that formed the black hole, along with everything that has fallen into it since, is compressed into an infinitely small point of infinite density. Whenever physicists encounter the word infinite, they become cautious. History has shown that infinities often indicate that a theory has reached its limit rather than describing reality perfectly. Newton's laws worked beautifully until scientists discovered situations where Einstein's equations provided a better description. Many researchers believe the singularity represents another such limit. Something deeper must exist. The challenge is that no one knows exactly what it is. Modern physics is built upon two enormously successful theories. General relativity explains gravity. Quantum mechanics explains the microscopic world of atoms and particles. Each theory works with astonishing accuracy within its own domain. Yet when physicists try to combine them inside a black hole, the mathematics refuses to cooperate. Gravity becomes unbelievably strong while quantum effects become impossible to ignore. Neither theory alone can fully describe what happens. This is why black holes occupy such a special place in science. They are not simply strange objects floating through space. They are natural laboratories where the known laws of physics begin reaching their limits. For decades, researchers have searched for a deeper theory capable of describing these extreme conditions. Some believe space itself has a tiny quantum structure, invisible everywhere except inside black holes and during the first moments after the Big Bang. Others propose that the universe contains additional dimensions hidden from ordinary experience. Still others suggest that the singularity never actually forms because quantum effects prevent matter from being compressed forever. No one yet knows which idea, if any, is correct. Then another mystery appears. Imagine throwing a library to the black hole. Every book, every photograph, every scientific discovery, every piece of music ever written. Everything disappears beyond the event horizon. According to quantum mechanics, information should never truly be destroyed. It can change form, become scrambled, or spread across countless particles, but the information itself should always remain somewhere within the universe. Black holes appear to violate that rule. Where does the information go? Does it disappear forever? Or is it somehow preserved? This question became known as the information paradox, one of the greatest unsolved problems in theoretical physics. The mystery became even deeper when physicists realized that black holes are not completely black after all. In the 1970s, Stephen Hawking made one of the most surprising discoveries in modern science. Using quantum mechanics, he showed that black holes should slowly emit an incredibly faint form of radiation. Over unimaginable lengths of time, this process causes them to lose energy and gradually shrink. Eventually, they disappear. Not after millions of years. Not after billions. But after times so enormous that even the current age of the universe becomes insignificant by comparison. Imagine a black hole surviving while galaxies collide, stars are born and die, and entire clusters of galaxies evolve across trillions upon trillions of years. Only after these unimaginable stretches of time would Hawking radiation finally erase the black hole itself. But that raises another question. If the black hole eventually disappears, what happens to everything that fell inside? For decades, physicists debated this problem intensely. Some believed the information truly vanished forever. Others argued that the laws of quantum mechanics simply would not allow such destruction. Even today, no complete consensus exists, although many researchers believe the information must somehow survive in ways we do not yet fully understand. The remarkable thing is that these questions are no longer philosophical. They are scientific. Every new telescope studying black holes, every observation of gravitational waves, And every advance in theoretical physics brings humanity a little closer to understanding what may truly happen inside these extraordinary objects. Our imaginary spacecraft has now disappeared forever behind the event horizon. No more signals reach the outside universe. Its final transmission has already traveled across space and been recorded by distant observatories. Everything beyond this point remains hidden. Not because scientists lack curiosity, but because the laws of nature themselves prevent any information from returning. Perhaps one day humanity will discover a complete theory of quantum gravity that finally explains what lies beyond the event horizon. Perhaps future civilizations will understand black holes as easily as we understand planets today. Or perhaps some mysteries will always remain hidden behind boundaries that the universe itself refuses to let us cross. Either way, black holes remind us that science is not simply about finding answers. It is about discovering better questions. And few questions are greater than this one. What truly waits beyond the point of no return? In our next chapter, we'll return to humanity one final time and ask the question that naturally follows everything we've witnessed. If astronomers discovered a wandering black hole tomorrow, could our civilization survive? Or would the fate of Earth always be unavoidable? After everything we have witnessed, one question remains impossible to ignore. If astronomers really discovered a black hole heading toward the solar system tomorrow, would humanity have any chance of surviving? Throughout history, our greatest strength has never been our size or our physical abilities. It has been our capacity to solve problems. We learned to cross oceans, fly through the sky, split the atom, and land machines on other worlds. Challenges that once seemed impossible eventually became engineering projects. So could the approach of a black hole become another problem to solve, or would it represent a limit that no civilization could overcome? The answer begins with something surprisingly hopeful. Time. Unlike an asteroid that might appear with only a short warning, a black hole would almost certainly announce its arrival decades or even centuries before it became dangerous. As we saw throughout this journey, gravity leaves clues long before the object itself reaches the planets. Astronomers would detect disturbed stars, changing comet orbits, and subtle shifts throughout the solar system years before Earth experienced any direct effects. Humanity would not be surprised. It would have time to prepare. The first idea people would naturally suggest is changing the black hole's path. After all, if we can redirect small asteroids, why not push the black hole away? Unfortunately, the numbers quickly become overwhelming. A typical stellar black hole contains several times the mass of the Sun. It is not simply heavy. It is unimaginably heavy. Every rocket humanity has ever launched combined would produce essentially no measurable change in its motion. Even our most powerful nuclear weapons would be insignificant compared to the momentum carried by an object like this. The black hole would not even notice. Perhaps then we could move Earth instead. Interestingly, this idea is not entirely impossible in theory. Scientists have proposed methods of slowly changing Earth's orbit over millions of years by carefully redirecting large asteroids to transfer tiny amounts of energy to the planet. Given enough time, small changes could eventually become significant. But against an approaching black hole, even that would probably not be enough. The problem is not simply Earth's location. It is the entire solar system. If the black hole passes close enough to threaten Earth, it will almost certainly disturb the orbits of the other planets as well. Moving Earth a little closer to or farther from the Sun would not solve the larger gravitational problem unfolding across the entire planetary system. Another suggestion often appears in science fiction. Hide underground. Deep beneath the surface, protected by kilometers of solid rock. Underground shelters work well against radiation, storms, and even many asteroid impacts. They do not work against gravity. If the planet itself is stretching under enormous tidal forces, every underground facility stretches with it. Rock cannot shield against changing gravity because gravity passes directly through everything. The Earth itself is what is being affected. Perhaps, then, humanity's only hope would be leaving Earth completely. Unlike hiding underground, this idea becomes more realistic the longer the warning period. If astronomers detected the black hole centuries before its arrival, future generations could devote enormous resources toward building permanent settlements elsewhere. The Moon. Mars. Large space habitats. Perhaps even generation ships designed to travel toward another star. Today these ideas remain extremely difficult, but they are no longer pure science fiction. Humanity has already begun learning how to live beyond Earth. Robotic spacecraft have explored nearly every planet in the solar system. Permanent lunar bases are actively being planned. Missions to Mars continue advancing year after year. A civilization given centuries of preparation would almost certainly become far more capable than we are today. Even so, another challenge immediately appears. Would Mars actually be safe? Probably not. If the black hole approaches close enough to destroy Earth, Mars would almost certainly experience major gravitational disturbances as well. Depending on the exact trajectory, much of the inner solar system could become unstable. The safest solution would likely require something far more ambitious. Leaving the solar system altogether. That sounds impossible today, yet so did crossing the Atlantic Ocean 1,000 years ago or landing on the Moon 100 years ago. Technology changes much faster than human intuition expects. Future propulsion systems powered by nuclear fusion or entirely new energy sources could make journeys to nearby stars far more practical than they seem today. Of course, no one knows exactly what technology humanity will possess centuries from now. But history teaches us an important lesson. Never underestimate future generations. The people who built the first airplanes could never have imagined spacecraft leaving the solar system only 60 years later. Likewise, we cannot confidently predict what civilization may achieve hundreds of years from now. Still, there is one problem technology alone cannot solve. Who gets to leave? No spacecraft could carry billions of people. Every civilization depends upon scientists, doctors, engineers, teachers, artists, farmers, builders, and countless others. Preserving humanity would require preserving far more than individuals. It would mean preserving knowledge, culture, language, history, and everything our species has learned across thousands of years. Perhaps the greatest challenge would not be engineering. It would be cooperation? Throughout this story, astronomers around the world shared observations regardless of nationality. Space agencies worked together because gravity makes no distinction between countries. A black hole threatening Earth would become the first truly universal challenge faced by every human being alive. History shows that humanity often accomplishes its greatest achievements when united by extraordinary goals. Building particle accelerators. Sequencing the human genome. Landing on the Moon. Exploring Mars. An approaching black hole might inspire the largest scientific collaboration our species has ever attempted. Would success be guaranteed? No. Current science offers no realistic method for saving Earth itself if a stellar black hole passed close enough. But saving humanity? That is a different question. Given enough warning, enough knowledge, and enough cooperation, perhaps civilization could continue somewhere beyond the solar system, carrying with it everything that once began on one small blue planet orbiting an ordinary yellow star. Fortunately, this discussion remains entirely hypothetical. Because despite everything we have imagined, one final question remains. Could this actually happen? Or have we simply followed one of the rarest possibilities the universe can produce? After traveling from the edge of the Milky Way to the center of a black hole, we finally arrive at the question that matters most. Should we actually worry? The answer is reassuring. Almost certainly not. Everything we have explored throughout this documentary is based on real physics. If a stellar black hole approached Earth closely enough, gravity would indeed reshape the solar system step by step. The disturbed comets, changing planetary orbits, growing tides, and eventual destruction of Earth all follow naturally from our current understanding of gravity. The scenario itself is scientifically possible. It is simply extraordinarily unlikely. The reason is surprisingly simple. Space is almost completely empty. Movies often portray the galaxy as crowded with stars packed closely together, but reality is very different. If our sun were reduced to the size of a tennis ball, the nearest star would still be hundreds of kilometers away. Most of the Milky Way contains almost nothing at all. That enormous emptiness protects us. Astronomers believe the Milky Way contains hundreds of millions of stellar black holes, yet the galaxy itself is so vast that the average one spends millions of years traveling through completely empty regions without ever coming close to another star. Our own solar system has orbited the center of the Milky Way roughly 20 times, since it formed over 4.5 billion years ago. During that incredible journey, it has passed through changing stellar neighborhoods, survived nearby supernova explosions, and experienced countless tiny gravitational influences. Still, Earth remained here. Life continued evolving. Civilizations appeared. Humanity looked up and began asking questions about the universe. If catastrophic encounters with black holes were common, stable planetary systems would be extremely rare. Instead, astronomers have now discovered thousands of planets orbiting distant stars, many of which have remained stable for billions of years. The universe is surprisingly good at giving planets time. That does not mean black holes are harmless. Far from it. They are among the most extreme objects known to science. They tear apart stars, collide with one another, and generate gravitational waves powerful enough to shake space itself. Somewhere in the Milky Way, there are undoubtedly planetary systems whose histories have been dramatically altered by wandering black holes. But probability matters. The difference between possible and likely is enormous. Perhaps the most comforting part of this story is that modern astronomy would almost certainly see such an object coming long before it threatened Earth. Space telescopes constantly monitor billions of stars. New observatories scan the sky every clear night, searching for tiny changes that might reveal hidden objects. Humanity is far more aware of its cosmic surroundings than at any point in history. We are not blindly drifting through the galaxy. We are watching, learning, measuring, understanding. And perhaps that is the greatest lesson black holes have to teach us. Not fear. Wonder? They remind us that gravity can bend light, slow time, and reshape entire galaxies. They challenge the limits of Einstein's theory while pointing physicists toward discoveries that have not yet been made. They force us to ask questions about the nature of space, time, and reality itself. In many ways, black holes are not the enemies of science. They are its greatest teachers. Our story imagined the destruction of Earth, but the real universe has given us something much better. Time. Time to explore. Time to discover. Time to understand. Tonight, as you look toward the stars, somewhere out there black holes continue drifting silently through the darkness exactly as they have for billions of years. Most will never come anywhere near us. They will continue wandering through the Milky Way completely unnoticed, following the same laws of gravity that keep Earth orbiting the Sun. Meanwhile, our small blue planet continues its own journey around an ordinary star on the quiet outskirts of an ordinary galaxy. From one perspective, that makes us seem incredibly small. But from another, it makes our existence even more extraordinary. Because as far as we know, this tiny world has produced something exceedingly rare. A civilization capable of understanding the universe. A species that can detect invisible objects thousands of light years away, predict their motion using mathematics, and imagine journeys to places no human will ever visit. The universe does not owe us explanations. Yet little by little, we continue uncovering them. Every answer reveals another mystery waiting beyond the horizon. Every discovery reminds us how much remains unknown. And perhaps somewhere, far beyond the stars, another civilization is asking the very same questions, looking into the darkness and wondering what would happen if a black hole ever came their way. For now, however, the night sky remains peaceful. The planets continue their ancient dance around the sun. Earth continues turning beneath our feet. And somewhere in the vast silence of the Milky Way, invisible black holes drift endlessly through the darkness, reminding us that the universe will always be larger, stranger, and more beautiful than we can ever fully imagine.